Let's look at equations for simple harmonic motion. First of all, what is simple harmonic motion? Simple harmonic motion, an example of that would be a spring oscillating system. So if I have a spring attached to a wall, I attach a mass to the spring, it's at the equilibrium position, the rest position. If I displace the mass either to the right or to the left, a certain distance, delta x, which we'll just abbreviate as x, then the spring exerts a restoring force. In other words, if I push it and let go, the spring is going to try to push it back to its equilibrium. If I pull it out and stretch it and let it go, the spring is going to pull it back to its equilibrium. And so we know that there's a spring force equal to negative kx. Now, x being a vector and spring force being a vector. So in the vector form of this equation, Hooke's law, the spring force equals negative kx. So if we look at the situation in a Newton's second law, the net force equals mass times acceleration. So what we have is negative kx equals mass times acceleration. And that looks all fine and good, but we see that acceleration, if we recall, is the second derivative of position with respect to time. So minus kx equals m times the second derivative of x with respect to time. And this is what we call a second order differential equation. Now, I'm not going to get into how to solve this differential equation, but one of the solutions to a second order differential equation is a sinusoidal equation. So, the solution to this is x is equal to a cosine of omega t plus phi. In this, amplitude is a. Amplitude means the maximum displacement. So the maximum delta x, the maximum displacement from the equilibrium position. Omega is what we call the angular frequency. Angular frequency. And phi here is the phase shift. So in this formula, x equals a cosine omega t plus phi. Now, we use the cosine. You could use the sine also, but we use the cosine because most often in these types of problems, at time zero, the position of the mass here is at its maximum. So in other words, I stretch it out, and at time zero, I let go. So at time zero, it is at the amplitude. And when that happens, if I use the cosine function, then the phase shift becomes 0. And so I end up with just x equals a cosine omega t. And that works out pretty well. In this formula, the angular frequency is represented by 2 pi times the linear frequency. Linear frequency just being the number of oscillations per second. If I multiply that by 2 pi, what I'm doing is I'm converting a linear frequency into an angular frequency, because there are 2 pi radians in one complete cycle, and therefore 2 pi times the linear frequency gives me an angular frequency. And I need an angular frequency because what that does, this is a sinusoidal function, and you can only do sine functions on angles. And so I can't just do cosine of the frequency times time, I have to do the cosine of the angular frequency times time. This converts this into an angular value, of which I can now use the cosine. Now, looking again at this equation, x equals a cosine omega t plus phi. The derivative of x with respect to time is the velocity, and so we end up with velocity, which is derivative of x, gives me negative a omega sine omega t plus phi, and the acceleration, which is dv dt, is the acceleration, that is minus a omega squared cosine omega t plus phi. Now, if I look at this function right here, minus a omega squared cosine omega t plus phi, I'm going to pull out some stuff here. So my acceleration is, I'm going to have the a here, and I'm going to have the cosine of omega t plus phi, and what I'm left with is a minus omega squared. So this whole thing times minus omega squared, that's the acceleration. And I notice that this function here, a cosine omega t plus phi, that's just x. So what I have is the acceleration equals minus omega squared times x. So good equation here, good equation here, good equation here, and this one right here also. These are solutions to simple harmonic motion for an oscillating spring system. Now, if we come back to this original, minus kx equals ma. So minus kx equals ma. And we remember that acceleration is minus omega squared x. I end up with minus kx equals m times minus omega squared x. Now, let's solve this for omega. The x will divide out, and the negatives will divide out. So let's get the m over here. So what I have is k over m equals omega squared, or in other words, the square root of k over m equals omega. Okay, so omega for a spring oscillating system is the square root of k over m. Now, over here I've got omega equals 2 pi times the frequency, right? But frequency, we remember, is equal to 1 over the period. And so the omega, which is 2 pi times the frequency, is also 2 pi divided by the period. Now, on the equation sheet, you'll actually see the equation period equals 2 pi over omega. That's the same thing here. Omega equals 2 pi over t. T equals 2 pi over omega. That's a good equation to know. But if omega is the square root of k over m, what I have here is 2 pi over omega is the same as 2 pi times the reciprocal of omega. So for a spring oscillating system, the period is equal to 2 pi times the square root of reciprocal this m over k. And that is my basic equation for the period of a spring oscillating system. Now, some other examples of simple harmonic motion include simple pendulum. Now, a simple pendulum is basically a negligible mass string with a weight at the end, and it is simply going to oscillate back and forth like so. So simple pendulum, a lot of the equations still apply, only this time the displacement is not a linear displacement as it was with a spring oscillating system. It is an angular displacement. So instead of using x as the position and v as the velocity and a as the acceleration, we use theta to represent the angular position of the pendulum equals theta max times the cosine of omega t plus v. So it's basically the same equation. Theta max, the maximum angular displacement, is another name for the amplitude of the simple pendulum. What kind of angle am I displacing it when I let go? Here the restoring force is the force of gravity. Omega is equal to minus omega theta max sine omega t plus v. Alpha equals minus omega squared theta max cosine omega t plus v. So you can see the form of the equations are very similar, but we're talking about angular displacement, angular velocity, angular acceleration instead of the linear variables. Now, the period equation for a simple pendulum is 2 pi times the square root of L over g, L being the length of the pendulum and g being the acceleration of gravity. Simple pendulum is a good experiment to be able to do to figure out the acceleration of gravity, and you can rearrange this equation to solve it for g. Another type of simple harmonic motion that you may encounter is what I call the physical pendulum, or the solid pendulum. Physical pendulum basically means I take a solid object, not a massless or negligible mass string with a weight, but let's say I take a uniform rod and I pivot it at one end. So here I've got this uniform rod and it's pivoted here, and I displace it, and it's going to then swing like so. Kind of like a pendulum, only it's a physical rod and it's not a simple pendulum with just a mass at the end. So for the physical pendulum, there is formula, period equals 2 pi square root of I over mgd. In this formula, I is the inertia, and for the inertia, notice it's not pivoting through the center of mass, so one needs to use the parallel axis theorem. Remember that I parallel equals I center mass plus mh squared. There's a nice video about this if you would like to review that. But that's how you find the inertia, okay? And here the d is the distance from the center of mass to the axis of rotation. That's what the d is. So I can find the period of a physical pendulum by taking 2 pi times the square root of I over mgd. Another example of simple harmonic motion is what's called a torsion pendulum. And a torsion pendulum, torsion basically means a twisting force. So a torsion pendulum would be, for example, if I have a rigid rod or a thin string here, and a cylinder is attached at the bottom, which if I displace it one way, that twisting is going to have a twisting restoring force. and the twisting restoring force, the torque produced by that, is equal to minus a constant times the angular displacement. So it's a twisting type of force with a twisting restoring force. And the period of a torsion pendulum is found by taking 2 pi times the square root of inertia over this torsion constant. And that is how you find the period of a torsion pendulum. Looking back at these equations of simple harmonic motion just in the spring oscillating system, we can see, because the sine and cosine function, they alternate between -1 and 1. They max out at either plus or minus 1. So we can see that x max, the maximum position, is the amplitude, that the maximum velocity is a omega, that the maximum acceleration is a omega squared. Again, so that's your maximum displacement, your maximum velocity, and your maximum acceleration. Now, another example of how simple harmonic motion problems are used is looking at the energy in the system. I'm going to again refer specifically to the spring oscillating system. But if I look at conservation of energy in the system, what I've got is it's the total energy is a combination of kinetic plus the spring potential in the system. Okay? Now, there is a period of time when the velocity is 0. Where is the velocity 0? Well, the velocity is 0 as the spring oscillating system here, if this is my equilibrium position, so it's oscillating between here and here, between here and here. So this is my equilibrium position right here. So when it reaches its maximum displacement, it's about to turn around, and for that brief instant, the velocity is 0. At that point, all of the energy is stored in the spring. So the total energy can be found by taking 1/2 k times the maximum displacement, and maximum displacement is the amplitude. So Ka squared, that's your total energy. Now, there's a time in the system where the spring is neither stretched nor compressed, and all of the energy is in kinetic energy, and that's as it's passing through equilibrium. So when it's passing through equilibrium, I know that all of the energy is kinetic. So it's 1/2 m times the max velocity squared. And as we just learned, the max velocity is a omega. So we can plug this in here for max velocity, and we see it's 1/2 mass times a squared omega squared. And so that is another expression for the total energy of the system. And anywhere you can find the total energy by adding the kinetic plus the spring potential. Those are the energy equations and how they relate to simple harmonic motion. You can do a similar thing as you're looking at a simple pendulum or a torsion pendulum or a physical pendulum. Look at the energy that's involved. With the pendulums, we're looking at the simple and the physical pendulum. You look at the combination of gravitational potential and kinetic. With the torsion pendulum, you've got basically a torsion force, which is like a spring potential, and kinetic as well, rotational kinetic in that case. Those are the equations of simple harmonic motion. I hope this has helped you understand those.